All right, in this module, we're going to talk about the Ewald Sphere. So the Ewald Sphere is a useful construction, a visual way of determining the necessary conditions to detect whether various crystal planes will diffract. So these conditions are the ones that we discussed in the last section on Bragg's law. But this is basically a graphical construction using what we call this Ewald sphere. And so the whole idea of the Ewald sphere is based on the reciprocal lattice, which we've discussed before. And so what the Ewald sphere is as you might have figured out, it's a sphere, and we will sort of represent it as a circle, but it's going to be defined by a couple points. And so if I just kind of draw a point here, and this is labeled A, so this is basically the center of the sphere, and it's where the crystal is located. So A is where the crystal is located. All right, so that's the center of the sphere. So I'm going to draw a circle because we're just showing a two-dimensional representation of it. So I've got my trusty device here with a permanent marker attached. And so I'm just going to draw a sphere with the center, or a circle with the center of A. Try to get it continuous. All right. So this is going to be my Ewald sphere. So I have my position A, the center of the sphere, where the crystal is located, and then I'm going to go to this point on the edge of the sphere, and this is going to be my origin. So I'll kind of put it like two circles, so you can see that that's the origin. So this is the origin. O is the origin of the reciprocal lattice. All right. So those are the kind of the 2 points. And so the I can kind of draw in what this reciprocal lattice might look like. Just an example here. And so let's say I've got points away from the origin. So these are all reciprocal lattice points. Trying to do my best to make sure it's a real lattice. So those are my reciprocal lattice points of my reciprocal lattice. So the first thing that we start with is by drawing the circle here, I've kind of assumed it's a certain distance. So the vector from A and then terminating at O, so this vector OA, so this is the radius of the Ewald sphere. And the important thing about the Ewald sphere and this radius is the radius is equal to 1 over the wavelength. So we use lambda for that. So in actuality, the wavelength that I've drawn here is dependent on the wavelength of X-rays that I'm using in the experiment, right? So I've kind of drawn it in the sketch just randomly, but that's tied to the reciprocal of the wavelength. So that's very important for this. And so this is also, so OA is parallel to the incident X-ray beam. So that vector that we have here is basically in the same direction as the X-ray beam. So that's an important part to mention here. All right, so the vector OA represents the incident beam originating at the crystal, point A, and then going to the origin of the reciprocal lattice. So let's look at the diffracted beam now. So the diffracted beam can be represented by another vector from A to any of the given reciprocal lattice points. So let's call this one B, and if we draw a vector from A to B, that represents the vector. So AB represents the diffracted beam for that point, for that given diffracted planes. So again, remember that point B, a point in a reciprocal lattice represents a vector from the origin to point B. That represents a set of planes in real space. So by saying that there's a diffracted beam at point B, we have a real space plane represented by B, right? So AB represents the diffracted beam. And so here's the important part about the Ewald sphere is that diffraction, as we've kind of specified by Bragg's law, only occurs, so those conditions for diffraction, so the necessary Bragg conditions that give us constructive interference, only occur when the reciprocal lattice point touches the surface of the Ewald sphere. So for point B here, you can see point B is on the surface of the circle, which is also in 3 dimensions a sphere. So since it touches the surface, it satisfies the Bragg conditions. And I'll kind of show you that sort of derivation in a second. But for now, any point that touches this sphere, the surface of the sphere, would satisfy Bragg conditions under this arrangement where we have the crystal here and the certain orientation with the reciprocal lattice as shown. So that's an important part to remember. All right, a couple other points I want to make about the Ewald sphere. So we've established the vector OA and AB. So these two vectors originate at point A, and the angle between them is very important for diffraction, and that is equal to 2 theta. So again, from Bragg's law, you remember the 2 theta term. So that's another thing that will relate this to Bragg's law. Also, if you take a vector from the origin to B, so basically the vector OB here, this is equal to DHKL star vector. So we talked about that in reciprocal space. So effectively, this has a distance of 1 over D. So we can say that this is, again, H A star plus K B star plus L C star, and it has the length, and it's equal to 1 over the DHKL vector. We can also view this a little bit differently too, is if we envision a vector that's twice as long as OA, so this vector, and so we basically put it on the other side of the sphere, and you basically draw a vector from that point to B. Try to do this the best I can. So if you draw it down here to B, and it's a little off, but just imagine I drew it to B, then this angle is equal to theta. So if you want to kind of visualize it in terms of theta, we can double the length of OA. And so if we want to think of this in terms of Bragg's law or an X-ray diffraction experiment, we're often scanning the angle to theta or theta. And so that's going to be the part by changing that angle that allows us to determine visually, using this Ewald sphere construction, whether diffraction occurs by essentially whether it touches the surface. So basically, B, since it's on the surface of the Ewald sphere, satisfies Bragg conditions according to Bragg law. What I want to do now is we've got this sketch of the Ewald sphere that we went over, and I want to see if we can derive Bragg's law very quickly using the Ewald sphere construction. Okay, so we have OA, that's the vector, and let's just look at the length. So let's look at the length OA. We know that is the radius of the circle, and we know that that is 1 over lambda. Also, we have the vector OG, and so here I'm defining G as the point halfway in the middle. So this is equal to the length of the D HKL star over 2. All right. So I know that sine theta, so again, going back up to the whole image here, this is theta, this is 2 theta. So we know that sine theta, we can show that that is OG over OA using basically using the triangle here, right? So this is A, O, and G, so we can basically use that triangle and determine that the sine of theta is OG over OA, and so that means that if we put those together, we get D HKL star divided by 2 times lambda. And also, we know that D HKL is equal to 1 over D HKL star. And so from there, we get that sine theta is equal to lambda over 2 D HKL. And if we rearrange that, we get lambda equals 2 D HKL sine theta. So this, missing it slightly. So rearranging that expression, we get lambda equals 2 HKL d HKL sine theta, and this is also, as you know, Bragg's law. So we've just shown that we can get Bragg's law from the construction of the Ewald sphere. All right, another point I want to make about this is if we look specifically in this region down here, we can notice that the vector from O to B is obviously a vector, so it's a line, but you can see that there's some curvature on the Ewald sphere, right? So the curvature of that Ewald sphere cannot sort of be neglected when we're comparing OB to that curvature. So this is what we see with the wavelengths of X-rays. But it's a little bit different when we look at diffraction from electrons, which will come up in electron microscopy later. And so for that comparison, I want to switch over to the slides really quick and show you the comparison between the curvature of the Ewald sphere for X-rays and for electrons. All right, so this shows you the comparison of two different wavelengths. So again, the radius of the Ewald sphere, so the size of the Ewald sphere, is tied to the wavelength, 1 over the wavelength of the radiation that you're using. So to approximate the wavelength of an X-ray, I've drawn this circle. So this is roughly the size of the circle that you would see from X-rays if this reciprocal lattice represents a typical tetragonal crystal. So again, you can see that the curvature of the Ewald sphere is obviously going to be to be huge. The curvature here is quite large between points. However, electrons are much higher energy and so have much smaller wavelengths, and so the 1 over the wavelength is going to be much larger. And so in comparison, this line that you see here, this actually represents a much larger circle. It's just so large you can't tell. So it's basically like being on the Earth's surface, right? If you're on that, you can't tell that the Earth's surface is curved, right? So the same comparison. So this is basically the Ewald sphere representing the electron wavelengths. So that's the difference. And just to zoom out a little bit, I don't know how easily you can see it, but that's right there is the reciprocal lattice. That little tiny circle is the Ewald sphere for an electron, and then this circle that I still can't get the whole thing in the frame is the Ewald sphere for electrons using their general wavelengths. So you can kind of see how much different the two are in these cases.